Let's take a look at our note. So take a look at this scenario, this case. Two sample t-test for the difference. Okay, we talked about the z-test. Now we're going to talk about the t-test. A two-sample t-test is used to test the difference between two population means mu1 and mu2. Well, first of all, sigma 1 and sigma 2 are unknown. You don't have information about the population's standard deviations. Samples are taken randomly. So far, so good. The samples are independent from each other. Okay, you don't have any issue here. And the populations are also normally distributed, or the sample sizes are large enough. Again, in that case, the test statistic that you're working with is the difference between sample means, which results in two scenarios. Okay, we're trying to find a standardized test statistic. The standardized test statistic, remember that when sigma 1 and sigma 2 are missing, is a t value, all right? But here you have two cases. The very first case happens when they give you this important piece of information that variances are equal to each other. They might say, hey, variances are not equal to each other. So for either of these two cases, you're going to find a t, but that t from variances equal to each other is going to be different from the t variances are not equal to each other. So again, if sigma 1 and sigma 2 are missing, you're going to find a t, but you need to find that piece of information in the example or in your project. Are variances equal to each other, or they are not equal to each other? If they are equal to each other, you're going to follow the standard error this way. If the variances are not equal to each other, then the standard error is going to be this scenario here. So your numerator is going to be the same. The difference between the sample means minus the difference between the population means, which is 0, divided by. Now for the standard error, if the project, if the boss, if the question says, hey, variances for the populations are equal to each other, you're going to calculate a pooled estimate of standard deviation sigma hat. What is that? It follows this formula. Sigma hat is equal to the square root of n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared divided by n1 plus n2 minus 2, and the standard error for the sampling distribution of the difference between sample means is going to be this guy that you calculated here, divided by the square root of 1 over n1 plus 1 over n2. Remember that since we are using t, they have to find the degrees of freedom, which is n1 plus n2 minus 2. Again, this is the case that the project says, hey, variances are equal to each other. From past studies, they know that the variances are equal. If, however, it says, hey, variances are not equal to each other, then your standard error, you don't have to find a pooled estimate of standard deviation. You just go directly and find the standard error, which is square root of s1 squared over n1 plus s2 squared over n2, and you're going to select the smaller of n1 minus 1 and n2 minus 1. Okay, let me write it in the note for you, so you have these formulas written next to each other. Erase this board and write this down here. So the very first scenario is sigma 1 and sigma 2 are given. So you're going to find z to be x1 bar minus x2 bar minus the difference between the means divided by square root of sigma 1 squared over n1 plus sigma 2 squared over n2. This is what we did. We went over one example. Now the second scenario is sigma 1 and sigma 2 are not given. Sigma 1 and sigma 2 are not given. Okay. In that case, if variances are equal to each other, if sigma, in the question they mentioned that, if variances are equal, your t is going to be x1 bar minus x2 bar minus mu1 minus mu2 divided by the multiplication of two radicals. The first radical is the pooled estimate of standard deviation, sigma hat, which is n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared over n1 plus n2 minus 1 multiplied by this first radical is multiplied by second radical 1 over n1 plus 1 over n2. The question says, hey, variances are equal. The project manager says, hey, variances are equal. If not, it says, no, there is no way that variances are equal to each other. Variances are not equal. You're going to find t, which is equal to x1 bar minus x2 bar minus mu1 minus mu2 divided by, I'll just divide by one radical, s1 squared over n1 plus s2 squared over n2. So for this guy, the degrees of freedom is n1 plus n2. Sorry, this is minus 2. n1 plus n2 minus 2. And for this guy, the degrees of freedom is the minimum of n1 minus 1, n2 minus 1. Let's take a look at one example. Okay, here we go. A manufacturer claims, guys, keyword, claims that the mean operating cost per mile of its sedans is less than, another keyword for you, less than, of its leading competitor. You, as a statistician, conduct a study using 30 randomly selected sedans from the manufacturer and 32 from the leading competitor. Okay, very good. So we have two samples. They are independent from each other. The results are shown at the table on the left-hand side. The manufacturer, the sample that you took, well, the mean is 0.52. The standard deviation of first sample is 0.05, and 1 is 32, the sample size. From the competitor, the mean of your sample is 0.55. The standard deviation of it, the second sample is 0.07, and the sample size is 32, everybody. Well, at 5% level of significance, can you support the manufacturer claims? Guys, this line is super important. Assume the population variances are equal to each other. The last piece of information is the information, the leading information helping us to choose the correct T formula. Assume the population variances are equal to each other. Very good. So let us take a look at our board, punch the formula, and do the calculation. Variances are equal to each other. It means that the ugly formula is this formula to use. Very good. So step one, our very first step is to write the null and alternative hypothesis. Remember the keyword? The keyword was less than. mu1 is less than mu2. This was our claim. The keyword less than. It means that this is our alternative hypothesis. Okay, we have a left-tailed graph. Now mu1 is larger than equals to mu2. This is your null hypothesis. So null and the alternative. With claim next. Very good. I have a left-tailed graph because my alternative hypothesis is less than. Okay, here we go. P-value is on the left side. P-value. Very good. Step two. Sigma 1 and sigma 2 are missing. Also, the question says variances are equal. These are the information that we got from our example here. So what's the meaning of that? It means that we are finding a pooled estimate of the standard deviation. So our T, the standardized test statistic, is equal to x1 bar minus x2 bar minus mu1 minus mu2 divided by the multiplication of two radicals. The first radical, n1 minus 1 times s1 squared plus n2 minus 1 s2 squared divided by n1 plus n2 minus 2 multiplied by the second radical, which is 1 over n1 plus 1 over n2. This is the formula that we're going to use. Well, I know this is my formula, but what are the informations that I need to plug in here? Let's go back to the note. x1 bar, s1, n1, x2 bar, s2, n2. These are the information that I need to plug into the formula. Let's take a look. So my T, or standardized test statistic, becomes, well, let's see. We have 0.52 minus 0.55, the difference between the sample means minus the difference between population means is 0. So you're going to write down 0 divided by square root of n1 minus 1. n1 is 30 minus 1. s1 squared. S1 is 0.05 to the second power plus, I need to continue this line, this radical plus n2 is 32 minus 1 times s2 squared. S2 is 0.07 to the second divided by n1, 30 plus n2, 32 minus 2 multiplied by 1 over 30 plus 1 over 32. Well, okay, the T is going to be approximately negative 1.93. This is my standardized test statistic, all right? So since it's a t-value, I need the degrees of freedom. The degrees of freedom is 30 plus 32 minus 2. 30 plus 32 minus 2. Okay, now what is the p-value? What is the p-value? Okay, let's do the calculation. So the p-value is about 3%, 0.03. And now is p-value less than equals to alpha? Alpha is 5%. Our p-value is 3%. Well, okay, 3%. So it's going to be less than or equal to 5%. Well, since our p-value is less than equals to 5%, what's the meaning of that? It means that you reject the null hypothesis, or since we are rejecting the null hypothesis, we are supporting the claim. So support the alternative hypothesis, which in this case is the claim. Support the claim.